In this video, we're going to develop kind of a nifty little theorem that has to do with the powers of an element of a group. So as always, let's let G be a group. Maybe abelian, maybe non-abelian, who knows? G is just a group. And let's let A be an element of G. Okay, in a previous video, we defined the order of A to be the least positive integer n such that a to the n is equal to the identity. And we might actually give a more formal definition of order. This captures exactly the same mathematical idea. There's nothing different about it. It's just a little bit easier to write proofs with. So here's another way of saying it. We say that the order of A is n if the following two things are true. Okay, so here are the two things. Number one, a to the n has to be the identity. In other words, this has to be an exponent that takes a to the identity. And number two, if m is also a positive integer and a to the m is equal to the identity, then m is greater than or equal to n, because we want n to be the least. By the way, this inherently assumes that n is a positive integer. If I don't make that assumption, this definition is a little bit wrong. Okay, so we're going to use this definition of order to prove a couple of nice things and important things to know about how the powers of a group element behave. So one thing we've been doing in a few of these videos is we've talked about what happens if we take a group element and we just start writing down powers of that group element and keep writing down powers all the live long day. We might even write down the zero power, which is the identity, and might even write down negative powers. So we're going to prove a couple of theorems that have to do with whether the elements in this list repeat one another, and if they do, how does that repetition work exactly? Well, it turns out it works in a very organized way, as we will prove. All right, so here is the theorem. So I'm actually going to prove this as a couple of different theorems. I think in Gallien's book, it's one theorem and it's split out into a few different cases. I actually want to make each case its own separate theorem. So here's the first theorem. If the order of A is infinite, okay, in other words, there is no positive integer n such that a to the n is the identity. Well, in that case, for I and j integers, and these can be n integers, positive or negative, we have a to the I equals a to the j if and only if I equals j exactly. Okay, so in other words, what we're saying is if the order of A is infinite, if A has infinite order, then if you look at this list here, the one that I wrote down just a minute ago, what this theorem is saying is really just that all of the elements in this list are different. Every entry in this list is a different group element. And the reason that says that is because we're saying a to the I equals a to the j. Two powers of A are the same only if they're the same integer power. That is, the exponents are the same integer. In other words, if the exponents are different integers, then these will be different group elements. So now let's prove this theorem. So what we're saying is if A has infinite order, you will never see a repeat in this list, which is kind of remarkable, actually. So here's the proof. Okay, so first of all, this is an if and only if proof. So I have two directions to prove. I'm going to start by proving this direction because I think it's going to be pretty straightforward. So let's assume I equals j. Then, well, a to the I has to equal a to the j because, well, these two powers of A are defined in exactly the same way if these are the same exponents. So I don't know if you would call that by substitution or what, but I claim that this fact is pretty straightforward. If you have the same exponent, then raising a to the same exponent is going to yield the same power. So that part's done. Just requires saying something. Okay, so now let's prove the other direction. So let's assume that a to the I equals a to the j. We will show that I equals j. I'm going to do this by contradiction, I think. I'm going to say, let's suppose it's not. So let's suppose that I is not equal to j. And without loss of generality, let's assume that I is less than j. Now, the reason I can do that without losing any generality is, well, suppose it's the other way around. Suppose it was j less than I. Then the following argument would work just the same, just with the roles of I and j reversed. So I'm just going to do this argument once. Okay, so how are we going to approach this? So we know that a to the I equals a to the j. Now, here's what I think the problem is going to be here. Before I just start embarking on a proof, I want to say a little bit about why I expect things to work out. All right, so what we're saying here is we have two powers of a, they're the same power, and the exponents are different, with this one smaller than this one. Now, here's what I think is going to happen. I think that means that, well, because I is less than j, that means j is equal to I plus k for some positive integer k. That's what it means for I to be less than j. Even if I and j are both negative, this would still be the case, that there would be some positive integer I can add to the smaller one to get the bigger one. And so where I think the contradiction is going to come from is I can rewrite a to the j as a to the I times another positive exponent power of a. And what's going to happen is, well, let's just see. So that means that a to the I is equal to a to the I plus k, because that's what j is. And that means that a to the I equals a to the I times a to the k by properties of exponents. But then look at this. I'm going to make one more little step here to make this as seamless as possible. I'm going to put an identity over there on the left, because now what that's going to allow me to do is use left cancellation to get rid of a to the I. So by left cancellation, or if you like doing it the long way, you can just multiply on the left on both sides by a to the negative I. By left cancellation, 1 is equal to a to the k. But k is a positive integer, and we said the order of a is infinite, meaning no positive exponent takes a to the identity. So we've got a contradiction here, because we wound up with some power of a non-zero, in fact positive power of a equaling 1, and that's directly contradictory to what it means for a to have infinite order. If a has infinite order, there is no power of a with a positive exponent that is equal to the identity. So that's where our contradiction comes from. So, well, what was it we were assuming for the sake of contradiction? We said I is not equal to j, therefore we must have I equals j. And I believe that's the end of our proof. So that's cool. So now we know, let's just zoom out here for a sec. We now know that this list of powers we drew earlier, if a has infinite order, then this list of powers has no repeats at all. It'll be an infinite list of distinct group elements. So this is when order of a is infinite. Okay, so now in the next video I'm going to talk about the case in which a has finite order, so stay tuned for that. That'll be the next theorem.